they're really equal to your free cumulants, to this free cumulants, to this connected correlation function. Exactly in the same way that we did in the exercise, yes. Here we're doing it for the same matrix. So it's not going to be 0. Yes, then it's going to be 0, precisely. Only loops are finite, thank you, yes. Yeah, that expression is the general expression if you have different matrices. Yes, they refer to the indices in the case in which you have different matrices, they refer to the indices of the matrix in that block. In this case of this example, yes, you only have A. So the formula, yeah. Yes, because, yes. Yes, that the index IB is just telling you which one of those matrices you have to consider. It's not a matrix element. It's just the index for the variable. You should have put it on top, not on the bottom. Yes. Yes, sorry. Your colleague is rightly pointing out to the fact that this may be IB1. This is just telling you which matrix do you have inside here. It's nothing to do with the indices of the matrix. Okay. Okay, but now you remember why we wanted, what was our motivation of today? The motivation was to understand correlation functions between many times. So let's say 4 times. So, and to do an example of this being the out-of-time order correlator that you are discussing in the lectures of John. Okay, so in order to predict this kind of correlation functions, clearly we need to go beyond the standard ETH. So you need to assume that there are correlations between the matrix elements. Why this is important? Because for a long time people argued that ETH was the equivalent of saying that the matrix elements were Gaussian. But this was kind of a misconception due to the fact that the summary ansatz only encodes correlations up to only 2. But as you see in the exercise we did, if you consider products of more matrix elements, you're going to have a different kind of correlation functions. It's just that it's not encoded in the usual summary ansatz. Okay, so this was done by Foini and Kurchan. Okay, let me first write the ansatz. So this is exactly using this local rotational invariance. Now we generalize the expression I wrote before to accommodate for energy dependencies. So now I'm going to say that, okay, I have these simple loops, okay? But now this kind of simple loops, they are a smooth function of some order n of the energy average and of all the frequencies. So I1, I2, omega, I2, I3, etc. Divide times the density of states at that average energy n minus 1. So I remind you that E plus was the average energy. Now we're taking n energy indices. So this is E1 plus EI2 plus EIN divided by n. And I'm going to use with shorthand notations some vector omega, which contains all the energy differences, AI1 minus AI2, Okay. So you see, this is exactly what we already did last time. So now, but here I have to take an hypothesis. So now we're dealing with matrix elements. So now my Aij are matrix elements of a chaotic Hamiltonian. So I want to keep the structure in energy as my ETH motivation, as we discussed a lot. So these are structured matrices in the sense that there is dependency on energy. And so I basically extend my toy model now to encode also for this energy dependency. So this means that at every order, I have to define a new function Fn, which encodes for new information. And this, as I was saying, is Foini Kurchan 2019. And then the other property is that if one of the index repeats, then it factorizes. And I'm not going to rewrite it just because there are so many indices, but okay, you have it. It's the same as this one. Okay. So this is in a nutshell the essence of this kind of full eigenstate thermalization hypothesis. Namely, to go beyond two-point function and allow the matrix elements to have more information. Now, from how somehow we proceeded, it should be clear that the kind of argument for why you have these correlations is that there should be, let's say, this holds if you have a random basis. So if the matrix is invariant under rotation, no? And here, what we invoked is this rotational invariance. Namely, if I have a matrix elements, I can rotate the matrix elements locally. And it's clear that if you believe this argument, then if a system is ETH, it should be ETH at all orders. So this kind of properties should hold up to an arbitrary order n. 1 second. What I want to say is that you're not going to have a system which is 1 or 2 ETH for which just the first and the second hold and the others do not. At least I think the kind of generic many-body quantum systems which are non-integrable and chaotic and have the level spacing, they're going to do this for every order. Yes, the question? Yeah, now we do the exercise to see it. So precisely here, if you want to study an OTOC, okay. So why do you need it? So if you want to study an OTOC, okay, and you take ETH, so okay, now we will do. But you do not have these correlations, you would obtain just the Gaussian result. You would obtain just information which is already at the level of two-point function. But clearly, this cannot be the whole story, no? You want, the world is non-Gaussian. There are things beyond two-point functions. And an examples where they enter prominently is exactly this, where you have this butterfly effect, or if you have a classical limit, you have Lyapunov exponents and things like that. There was another question I saw. No. Okay, so let's do this exercise. So let's try to put this machinery to work in this case. So here, importantly, okay, I'm going to take, importantly, actually not very importantly, but I'm going to take an equilibrium distribution at some fixed energy, and for simplicity, I'm taking the thermal one, but I can take some microcanonical shell. It's also okay. So here you have to sum over 4 matrix elements, e to the minus beta ei over z. And then you have A of t, I1, I2, A, I2, I3, A of t, I3, I4, A, I4, A1. Okay, and now if I want to use ETH, I have to start distinguishing all the kind of possible arrangements of the indices. So what I want to do is that I want to sum with now different indices all the possible arrangements. So okay, let me write this in front. So I have a contribution in which all the indices I1, I2, I3, and I4 are the same. Yes? I1. Pardon. So I have one in which all the indices are the same. I1, 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 I1. Then I have to consider, for instance, the contribution in which 3 of them are the same and 1 is different. Now, in this kind of decomposition, okay, let me put here the one in which they're all different. So I1, I2, I3, I4. And it's useful to put the time dependency on the matrix. So you remember, the matrices live on the edge which connect to energy indices. So here I have time t, and here I have time t. Okay, I didn't write it explicitly here. It's diagonal in energy, the time dependency, but I can represent it on the edge, just to keep. So in this case, the indices are all different. Okay, then I have all the contribution that we wrote down before. Which other did I want to put? Here you have time, and then you can have those in which these two indices belong to the same block. And then also you can have crossings. I1, I2, I1, I2. Okay. So to put ETH to work, you have to sum over all the possible diagrams. There are others here that I didn't write down. Yes. You're going to see. Sorry, these diagrams, I mean that these, when I make the blob like this, the dot, then it's a matrix diagram. But you will see, and I try to use different colors. Maybe that didn't work, but okay, these they should be dashed. But you're going to see that they relate to the others when you go on the dual. But just give me 10 minutes. Okay. So here, this is just a bookkeeping. Up to this point, I'm just doing a bookkeeping of my diagrams. So you can call, yeah, these are, thank you for the question. This is really are just the ETH diagrams, and I'm trying to keep track of all the possible contributions. And you see from this that it kind of, this full ETH is kind of hopeless, no? Because you say, every time I have to sum over all the possible diagrams, it's kind of a mess of a calculation. I'm not very motivated to continue, no? But then, if you really stare at them a little bit more, you find that there are 3 types of diagrams. So there are these which are these simple loops, which are the ones that are bringing the new information, no? So they are the ones which are encoding the smooth functions at order n. Then there are the non-crossing diagrams. And then there are the crossing. And now actually for Yin and Kurchan, these crossing diagrams, they can also be seen as cactus diagrams. So imagine now you pinch the index all in the same spot. So this is equivalent to this. A little flower. Here you have a little fish. Okay. Okay, all these non-crossing, they can basically be written as simple loops which only have one, which touch only one point. Of course, they are the same. Okay, I mean that's okay. So you would like to say you're kind of hopeless, but then what you find is that actually these ETH properties, namely this scaling and the fact that these functions are smooth functions of the arguments, mean something precise on this diagrammatic bookkeeping. So let me call them some full ETH properties. Okay, so the first one, the property 1, is that actually crossing diagrams are exponentially suppressed. So let's do it for that diagram, such that also what I've been saying makes a bit more sense. So how should I interpret what I wrote before? So that is the sum over I1 different from I2. I only have 2 indices there. So here I have e to the minus beta ei over z. And here I have a, I1, I2. Then I have a, I2, I1. And then I have the same, a, I1, I2, a, I2, I1. Okay. This basically is this. Okay. Now, let's use the second property, namely that if I have one of the index that repeats, these are the leading order factorizes. So basically, what I can write that this is equal to this square. So and I have to put how much. So how does this depend on the energy density? So that will give me the density of states to the power minus 2, and then the smooth function at the second order squared. Okay, so I'm using ETH here. Actually, there is also the time dependency, but okay. Now at this point, let's count how many. Let's make some estimate on how big is this thing. So here I'm summing twice over the Hilbert space. Can you see? So I want to give a rough estimate on how big is this thing. So here I have the double sum over the Hilbert space. Each sum gives me a factor d. Okay. I'm summing over the two of them. Then here I have the density matrix, and this you can think about it as being 1 over d, because for instance, in the case of infinite temperature, so for beta equal to 0, this is just 1 over d. Okay, so this is not the normalization. It's supposed to be d to the minus 1, no? It counts with d to the minus 1. And then you have d to the minus 2. So in total, you have d to the minus 1. And since the dimension of the Hilbert space, or let's say if you can redo it also with a better estimate, namely putting inside here the density of states and then estimating, this at most becomes the density of states minus 1. And so this is exponentially small with the system size. Okay? So the crossing diagrams are exponentially suppressed due to ETH. And this already tells you something nice, that out of all these diagrams, we only have to consider the non-crossing ones. Yes? Yes, you have to do like this. First, you have to write I1, I2, I3, I4. You have to induce an ordering. And then once you do that, you start considering all the possible arrangements. And once you've done it, this is crossing. Because you remember, this is A1, this is A2, this is I1, and this is I2. Did I make a mistake? Yeah, this is probably. Okay, so this is sum. Here you have to read A, I1, I2. Here you have A, I2, A1. Then you have A, I1, I2. And then you have A, I2, I1. And then, okay, this T is just because that's inessential for the argument. Ouch. Okay. Yes? Yes, because you remember, ETH comes with some entropic contribution. Yeah, but you have two of them. You have A1, A2 squared. So each of them, so ETH is telling you that AJ, AJI, if these are different, is D to the minus 1, F2 of omega. So you take the square. No, but thank you, because this is precisely the point. So at this level, this is just an entropic argument. You are contracting too many indices, so you're not too many indices to respect to how big are your matrix elements, so you do not obtain something finite. This doesn't happen here if D is large enough and if you're in the chaotic case. Then we can discuss that there are subtle places where it can enter. If you're looking at, okay, no, thank you. So let's say your colleague is asking, okay, this is small, but we already saw that things which are small can be of the same order of other things. So of course, okay, this is small, but it's D to the minus 1. So is it possible that you're looking at things so that you're comparing it with other things which are of order D to the minus 1? This is the question. And now, when you look at traces, like this kind of expectation values, these are constructed to be of order 1. So when you look at things which are of order 1, this thing is exponentially suppressed. But then, if we are going to look at regimes where these correlations become very small, this can become dominant. No. So let's do the second property. Maybe it convinces you. Yes. Yeah, now I will do it. So let's do the free full ETH property 2. So which one did I want to do? Okay, I want to do the little flower, but you have you have 3 exercises in which you have to compute many of these other diagrams, so to really be convinced. But let's do the simple one, namely okay, this one. So what is this? This is now sum over I, e to the minus beta ei over z. By the way, this is basically the same as the exercise that, one of the exercises that I'm sure you have all done at the order 2, so now, okay. Right, it's clear why this is the contribution coming from this. So here I have I drop the 1 too. Okay, so I use ETH, namely that at the leading order these objects factorizes, and now this is full ETH, so now this is a smooth function of the energy. This is just ETH for 1 point. So this is a sum over I e to the minus beta ei over z, a of ei 4. Okay. And now this becomes, I pass from the sums to the continuum. So this is e to the minus e to the s of e minus beta e divided by z, a of e to the 4th. So this is equal to a of e beta to the power 4 plus n to the minus 1, which is equal to, so this was the thermal one of 1 point function, no? So this was, okay, so we discussed this is this to the power 4. So this is basically the sum over the simple loop of 1 order to the power 4. And you see, this is something order 1, okay? So as long as you look at things which are of order 1, this object is exponentially suppressed. And note that here I'm making also a much bigger mistake, a much bigger error. So there is this order n to the minus 1. This is much bigger than exponentially recta crossing. And in fact, going to the question that there could be situation, this is kind of a subtle question in one of the exercises, there could be class of observables where these actually, this 1 over n contribution becomes relevant. Okay, this is a bit subtle, and if you want, you can ask me later. Okay, so in exercises, you have to do all sorts of different diagrams just to, it's the same, but. So now, what is the precise statement? So this is telling me that if I have to neglect the crossing, I can basically look at this diagram in its dual. So let me put now the crosses on the edges. Okay, and the dual is when, let's say, these 4 are in 4 different blocks. And I know that this diagram contributes with the product of C1 to the power 4, which is precisely this. Okay. So now the precise statement that we can make is the following. So not only the combinatorics of multi-time correlation function is the same as free probability, let's say, so it's given by non-crossing partitions, but it has the same, due to the factorization of these non-crossing diagrams, I can really make an identification between free cumulants and the smooth ETH function above. In other words, I can always define now some thermal free cumulant. Let me do it for the AUTOC, no? A of TA, beta, or no, let me do it in general. AT1, AT2, beta, which is, and I can always define thermal free cumulants in this implicit way. So I can always give an implicit definition of free cumulants. They are a connected correlation function. You can do this for chaotic system, but also for integrable systems, for MBL system, for everything. Now, the precise statement that we're doing here is that the free cumulants defined in this way at every order n, so of A, T1, A, T2, so these that have this kind of unpleasant definition in which you have to draw all the diagrams, blah, 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 thanks to ETH, they reduce to simple loops. And this is true at every order. So thanks to ETH, you can write them as the sum over different indices of the matrix elements. And here I have the density matrix. Plus corrections, which are order -1. Okay, this is the precise statement. Due to ETH, so this is the ETH result. That free cumulants encode immediately your correlations between the matrix elements, because if you're summing over distinct indices, you get precisely this object. I'm going to repeat this. Well, in ETH, you never really need an average because you're summing over many of them. So, there was another question? Okay. Does it matter? That's a question for you. So it's good to keep track of the time dependency for your exercises, but once the indices which are pinching, they lie on the same time dependence, this floop, it goes away. Yes. Yes, yeah, absolutely. Yeah, that's, thank you. Yeah, that's absolutely. Yes, this is precisely the idea. So first of all, thank you for spotting that. First of all, you could have argued, as some people would be tempted to say, okay, Silvia, that is exponentially suppressed. Why are we talking about it? No? But it's exponentially suppressed Yet I'm summing over exponentially many of them, no? And things are such that this kind of entropic contribution, it's designed in a way that it gets reabsorbed. So at the end you get things which are of the order of 1. And indeed, if you're not summing over enough indices, you have this. No. Okay, it's gone. The decrossing, it's gone. The decrossing vanishes. And the crossing vanishes. Otherwise, yes, the loops contribute for this reason. Okay. So this is let's say the main kind of result, and then you can show. And I wanted to do it, but there is no time, so it immediately becomes an exercise. So if now you put these ansatz here, you do what we did here, not just for more variables. You pass from sums to integrals, and then you change variables, and you go into the average energy and the energy differences, and then you do the saddle point, okay? This becomes e to the I. So it becomes the Fourier transform. So here t is equal to t1, t2, tn. This becomes immediately the Fourier transform of precisely the smooth function of ETH. And here there is some factor. So now the point is that the smooth functions that appear in the ETH ansatz are precisely related in the large n limit to the Fourier transform of the free cumulants. So ETH, so going back to, so this we did not discuss it. It appeared also at the level of 2-point functions. Is let's say the fluctuation dissipation theorem. It's not. It's irrelevant. So it's not irrelevant. I mean, but okay, not for what we're seeing. But so it's not this thing. Okay. The smooth free function are dictating exactly the, let's say, the free cumulants now of time-dependent correlation functions. But now there is time dependence. So these are kind of local free cumulants, you may call them. So now let me just in these last 5 minutes, let me just maybe more chatting than writing, telling you how this relates to the question that we were discussing before of freeness. No? At this point, the matrices can be also the same. So all this point of conversation was just recognizing that free probability somehow helps us in the calculation of multi-point correlation functions, but not much else. Let's say it's about calling these objects with the proper name, free cumulants. Now I know what they are. They are free cumulants, but okay, it's not giving me a lot of other information. But now I can ask this question. So does my time evolution imply freeness? So in other words, and this is something you have been discussing, and you will be discussing also with in the other class with John, is how much my time evolution. So now we are considering matrices which are like this, no? So they are, if you wish, u of t, a, u dagger of t, no? Where this u of t can be either e to the minus iht, or can be a Brickworth circuit, no? Or whatever you may like. And now you can ask this question, so when is in what sense my time evolution is really chaotic? So what does it mean to be chaotic? What are the universal features? And I just gave you this definition that that B and A of U, when they're free, this implies, so A, B. If all their mixed free cumulants vanish, in the large D limit. So now we can ask the same question, namely, does chaotic time evolution lead to freeness? And if you're a bit skeptical, you can say, why? I mean, why would I care? But now we saw that there are several reasons to be interested in objects with alternating moments, no? Alternating time evolution, and so T0, T0, this kind of out-of-time order correlator that you have been discussing. So if A and B so if time evolution leads me to freeness, I gain a lot of information about how to compute mixed moments and other things. And so, yes, I want to erase this. So now what we can, and note that in general, time evolution of this form is very different from the R ensemble. So what I also told you is that if U is a sample with R ensemble, these two things are free. Okay, but chaotic evolution with an Hamiltonian is different from the R ensemble, even at infinite times, just from the fact that it conserves the eigenstates. So there is much more structure, energy is conserved. Yet what you can show is that this leads to freeness, and the kind of we have the whole equation above there, because what we just said is that the free cumulants in ETH, so of alternating variables, let me do it for an alternating, but you can show it also. Okay, so this is given by the sum over different indices, I1 different from I2 different. And here, now I want to put the energy dependency in the proper place. So here first I have I1, I2. This is e to the I, EI. Okay, I will take it later. Times. Then you have I2, I3. Then you have I3, I4. This should have the time dependency. So this is plus A3 minus A4. Okay, and you continue. So here I just wanted to write explicitly the time dependencies. From the phases, it's not very clear. Let me rewrite it. Okay. Because I have the time dependency only on the alternating ones. But now the important thing is that due to ETH, this corresponds to the average over distinct indices. So these energies, they're all different. Okay. And now I want to see what happens at t going to infinity. But as we saw, a way to let's say, take an appropriate average at t going to infinity is to take the infinite time average. So that we defined In this way, you take the limit of t going to infinity, 1 over t, and the integral. Okay. So let's take this infinite time average. So what I have to do is that I have to take the infinite time average of this object. Okay, in dt. And now we argued that somehow when we have oscillating factors of this kind, the only possibility to have something finite is that, let's say, these indices are permutations of these others. So that basically to have EI1 plus EI2 so this infinite time average selects only this kind of contributions. Okay. But now my system is chaotic. So we already said that a very fair approximation is to assume absence of degeneracies. In other words, to assume that you have no resonances. So if you have no resonances, the only possibility that you have such an identification of sums of energies is that this kind of indices are a permutation of the one below, namely that this is really coming from, if you have 2, just I equal to j, okay? But here the sum is restricted to different indices. So this integral is 0. Okay, no, I went very, very fast in this derivation, but let's go back to the question. Now, we want to see whether time evolution, even if it's very different from the R ensemble, has somehow some similar property, can lead to freeness. And the way to check if you have freeness is to look at the free cumulants between mixed variables. And so what we did, we computed we know that thanks to ETH, we know how to write the free cumulants thanks to ETH. And then what we showed is that by taking the infinite time average, these free cumulants vanish. So in other words, we have seen that time evolution of chaotic Hamiltonians, so if ETH holds, then time evolution leads to freeness. So chaotic time evolution is equally good as the R ensemble to lead to freeness at very long times. This may be too much. So this is somehow in the spirit of looking at correlation functions, and what you expect is that correlation functions A of TA connected will go to 0 at long times, no? Will vanish at long times. And now what we are saying is that all the free cumulants are going to go to 0 at long times. So, and the mathematical way to say this is that the matrices become free. So time evolution makes observables free. Yes? Yes, I mean, people in quantum information have been studying this kind of questions from the point of view of unitary designs. So instead of taking really the R ensemble, they take ensemble of unitaries which look like R, but only up to order K. So in that sense, you can say that a K design, leads to K freeness. So it makes observable free only up to order K. And you may note that K-designs are very different from Hamiltonians, Hamiltonian evolution, but they are equally good in making observables free, asymptotic free in this large limit. Yes? Yes. Yes, I mean, this, the same statement of this being a mathematical tool hold in the sense that this is a bit, this is a mathematical statement of sending t going to infinity, but in physical systems, you're going to see this kind of free cumulants to go to zero at a finite time. And understanding really the way, let's say, this kind of freeness appears and the physical time scales associated to it is matter of discussions and research right now. So I think we should conclude because this is the time has come. But I just wanted to say, okay, this is kind of a very fresh field. ETH has been established for more than 20 years, and people were very happy with it by doing numerics. But understanding higher order correlations is let's say, gave a new impulse to the field, and there is a lot to be understood. Simple questions is how will this breaks if you do not have integrability, or how do you include locality, which is the other thing that you have been looking at on top of these pictures, and these are important and open questions, so they're good to keep in mind for a young audience. With this, I thank you for the attention.